thank you once again for enduring me. I guess this is 3 times now. It is a privilege to talk and to have an opportunity to address you about the sun. I'd like to dedicate this talk to my mother, Jacqueline, and actually she, maybe like a lot of our mothers, taught me the most important lesson. And we're all trying to learn lessons here, but the lesson she taught me on her knee was to love. Now, when we consider the sun, currently it's viewed as a gaseous plasma, and I'm going to advance that from the photosphere down, or to, after hearing David's talk last night, from the photosphere in. I didn't hear the whole talk, unfortunately, just the part, but from the photosphere in, the sun is condensed matter. And in the corona and the chromosphere, you have a combination of condensed matter and plasma. Now, the first proponent, actually, of the gaseous sun was Herbert Spencer. He was a very prominent evolutionist. His works were largely ignored by astronomers, but he got into quite a few little scuffles, and if you're interested in the history of how the sun became a gas, the citation is listed here. But the real person who gave us a gaseous sun actually was Father Angelo Secchi. He was just a spectacular astronomer. And if anybody has the chance, online you can see his books, Le Soleil, they're in French. And, but even if you can't read the French, look at the figures. They're phenomenal. And also Hervé Faye. So the sun really became a gas in the minds of these men in the 1960s, and many prominent men of the time in physics. So we can say that around 1965 is when the idea that the sun was a gas was really born. Now for Herbert Spencer, it wasn't fully a gas. It was kind of a bubble. It was a gas inside and it was condensed matter outside. For Faye and Secchi, the sun was a gas that had floating solid particles on the photosphere because they wanted to have the thermal emission spectrum. But what happened with Faye is something quite important. It's here that the sun lost its surface. So when you talk to an astronomer, they tell you, well, the sun doesn't have a real surface. It's an optical illusion. And of course, we can use mathematics to justify that. But the idea actually goes all the way back to Hervé Faye in an article he wrote in Le Monde in 1865, which I translate here for you. So then the exterior surface of the sun, which from far appears so perfectly spherical, is no longer a layered surface in the mathematical sense of the word. The surfaces, rigorously made up of layers, correspond to a state of equilibrium that does not exist in the sun. So surfaces do not exist in the sun. This limit is in any case only apparent. So since 1865, we've thought that the sun does not have a surface. Now, actually, some observational astronomers didn't agree with that. And there were arguments about the sun, did it have a real surface or not? You could find papers into the 1900s. Until then, there were papers by Schuster, Schwarzschild, and of course Eddington, and the sun then became fully gaseous, or been viewed mathematically as fully gaseous, and the observational astronomers just lost that battle. So today, if you look at the present model of the sun, we have a core, and in the core, it's thought that all the photons are produced. And why do we know that? Because of Kirchhoff's law. Of course, I just showed you that that is no longer valid. You cannot produce photons in the core of the sun. And then we have other layers, the radiation zone, the photons are leaving the core and they're radiating out, then we have convection zone. And eventually, for the gaseous sun, it takes millions of years for photons to finally escape here and give us an emission spectrum. Now this can be justified using Stefan's law, the center of the sun being very, very hot. If you say that the amount of photons that you get moves with temperature to the 4th, and you really believe that the surface here is at 5,000 Kelvin, and that's temperature to the 4th, you'll see there's an enormous amount of photons produced here. So this has to be considered enclosed, and that's how they felt that the sun could follow Kirchhoff's law, that it could be considered enclosed. Now the question for us is, does the sun really have a surface? And there's so much evidence about it, and people have said it a long time ago, there's no question the sun has a surface. And as soon as it has a surface, it cannot be a gas. So we have prominences and coronal mass ejections that can rise from the surface and come crashing back down. They represent real structures, and they are not optical illusions. So this is a little movie here, and you're going to see a coronal mass ejection. It comes back down, and it crashes onto the sun. And when it does, you see all these bright points lighting up. So this is a collision that's taken place. There is a boundary there. It's not just an optical boundary. It's a real boundary. So I'll let you see it again. Now here's another line of evidence that the sun has a real surface. We have Carrington rotation on the sun. We've known this since the 1800s. So the sun exhibits differential rotation on the surface, as first highlighted by Carrington when he was observing sunspots. But the coronal winds are orthogonal to this direction. And because they're orthogonal, this requires a physical boundary. So this is one of the simplest proofs. Because you have this orthogonal displacement of matter, you must have condensed matter there. A gas cannot do this. So another example was high energy flares, where it was discovered that if you get a very, very high energy flare, like greater than 10 mega electron volts, they were found to occur always towards the limb. So this shows that this is an anisotropic process, and again, evidence. So anisotropic means it doesn't occur in all directions. In other words, you're not sending X-rays out in all directions in space. It's preferential in one direction, and that requires that you have a surface. Now, to explain this, the gaseous models say, well, look, we have magnetic field lines that are coming in, and then we have a mirror plane, and then the mirror plane causes a reflection, and then this gives us our directionality. Of course, their mirror plane is my surface. Now here, this is an example from X-ray. So if you look at the sun in X-ray, what do you see? If you look at the line intensity is about 1 over the entire radius of the sun, over the entire disk, except at the limb. Exactly at the limb, as soon as you cross the surface, the line intensity doubles. And if you think about that, that means you're sampling twice as much atmosphere all of a sudden, and this shows that you have a discrete surface when the disk ends. So we see it in X-ray. Basically, at every frequency band, we see it. Now, this is a nice, simple line of evidence, and some of you know that I took an ad out in the New York Times in 2002 and said the sun was a liquid. And people really got a laugh out of it, and I took a lot of heat. Of course, the New York Times article, I did that under the advice of a very senior professor, which chooses to remain hidden from history. But this was one thing that I cited in that New York Times article, this particular figure. And this figure is important because it shows transverse waves on the sun. So this is a Doppler image. You're seeing a flare coming out in white at you in the upper left. So as the flare comes out, you start seeing transverse waves produced on the surface. And transverse waves can only exist in condensed matter. Gases cannot sustain such waves. And this, by the way, is over millions of meters. And so the wavelength here is millions of meters. This is definitely not a gas. Now, one of the things is solar physicists are troubled by limb darkening, and how do they explain it? And I'll show you that in a minute. But the sun is brighter at the center, and then it darkens as you go towards the edge. As you go towards the edge of the disk, it looks darker to us. Okay? For the gas models, we justify this using optical depth. But I'm going to explain to you that this is actually a lattice effect caused by directional spectral emissivity, which is well understood in the laboratory. We don't need optical depth to explain this. So in the gas model, what are they saying? When you're looking straight at the center of the disk, you're looking deeper into the sun, so it appears hotter because of the laws of emission tells you that that's going to look hot if you look deeper, so therefore it's brighter. But when you look at the edge of the sun, you're not looking as deeply, so now it looks cooler, okay? So this is the optical depth argument, which doesn't work, and you could read this paper. Again, one of the reasons this doesn't work is because Kirchhoff's law is not valid, so you can't get blackbody spectra this way. The fact that you can see differentially into the sun shows that Kirchhoff's law cannot hold. So anyhow, you could read this paper. Now, I've explained it this way by saying that the sun has a true lattice. So when you look at the photosphere, it actually has not only a true lattice, I want specifically this lattice. I want a lattice where the hydrogen atoms, so the sun is primarily made out of hydrogen, and I want to arrange the hydrogen in this structure. And the reason is because this is the structure that graphite adopts. So hexagonal layers, one on top of the other. Now, I didn't propose this structure in 2002, but I have been saying the sun has been a liquid since 2002, at least the photosphere, and that has been, as I first said in the New York Times, then other articles and papers. Most of the work you'll find from 2011 until present, I think I produced 20 papers last year. All I did was sit at my computer and just write. So you can find a lot of papers, and the most important paper to read, which condenses everything, is this paper on a building block for liquid sun, and another paper, 40 lines of evidence for condensed matter. So what is directional spectral emissivity? Well, this is actually important to this society. The emissivity of a material depends on whether or not it's a conductor. So if it's a non-conductor, its normal emissivity will start high, so it's up here, and then as you increase the angle of viewing, the emissivity drops. If it's a conductor, the normal emissivity is low, and then as you increase the angle, the emissivity goes up and then finally drops. You could read about that in the papers described below. Now here's an example from the emissivity of granules. Now granules, of course, are substructures on the sun, and they're what most of the surface is made out of. And granules are best explained by Baynard convection. That's a surface-driven process. So if you don't have a surface, you're not going to get Baynard convection. So you have convection upflow coming through the center of the granule, and then it recedes on the edges. Okay, so it looks like a little mountain. So what does that mean? Well, if we go back to our plot again, what we know is that on the angle, when it goes down, we're increasing the angle. So as it goes down, it's going to be dark. So we're going to have these dark intergranule lanes, and that's exactly what you see. It looks dark. You have these dark intergranule lanes. Now in the gas model, they say, well, that's because the temperatures are different. This temperature is different than that one. These are all different temperatures. Every time you see a different color. I say no, the temperature is pretty much the same, or the energy content is pretty much the same, but the emissivity changes because you've changed the direction that you're looking at it. Here's an example from sunspots. Now for 100 years now, they've been telling us that sunspots are cooler. The umbra of sunspots are cooler. Now, the first thing about sunspots is they're a manifestation of a real structure. They're not optical illusions. So if the surface is an optical illusion, you surely can't have a real structure. They are magnetic in nature. This is well known. And that's indicative that they're highly conductive. Their emissivities are best explained by directional spectral emissivity in conductive materials, not solely by temperature. So you're not really looking at a temperature effect here. The reason that the sunspot appears dark is seen in the lower figure here. See? These materials are at the same temperature, but this one's a conductor. So its emissivity is going to be low, just like silver has a low emissivity, right? So that's why the sunspot appears dark. It's not because it's cooler. It's because it's more conductive. Now this one is going to be harder for you to see. I couldn't find a good slide of a faculae. But for you who know what a faculae look like, you know that we see the faculae. You can't see them on the center of the sun, and they start appearing more as you move towards the limb. They become very obvious towards the limb. If you look at this figure carefully, even on the web, you will see it. So faculae are a manifestation of real structure. They're not optical illusions. They have elevated magnetic fields, which also indicates that they're formed from conductive materials. Their emissivities are best explained by directional spectral emissivity, again, in conductive materials. So again, we're looking at the sunspot. At the center, you don't see it much, but all of a sudden its emissivity increases, and now it starts looking white to us. And then as it goes towards the limb, the emissivity drops. Now to explain this, the gas models have to say that faculae have hot walls and cool floors. Well, the floor can't be cool because it's supposed to be hotter as you go inside the sun when you look at the limb darkening argument. And also, how do you get a hot wall in a gas? So it's very, very simply explained just by going back to solid state physics, and let's look at how conductors and non-conductors emit, and this general rule can explain all these phenomena using a single explanation. Now, as I've said in my talk on Kirchhoff's law, the Achilles heel of the gaseous sun is this spectrum. There is no way that a gaseous sun can produce a continuous solar spectrum. But nonetheless, even in 1865, people were saying that the continuous spectrum of the sun can be produced by a gas. And remember Balfour Stewart? He's the person who did Stewart's law. So remember, Kirchhoff was wrong about his law. Stewart was right, but Stewart wrote this paper saying that a gas could produce the continuous spectrum of the sun. So from all this, it was inferred that the luminous photosphere is not to be viewed as composed of heavy solid or liquid matter, but rather of the nature of either a gas or a cloud. So he says a gas can account for that spectrum, and that's not correct. Here's another one from 1869, Franklin and Lockyer. I mean, for people who know their science, they know that these are big names. The gaseous condition of the photosphere is quite consistent with its continuous spectrum. And this condition has, the possibility of this condition has already been suggested by Stewart, Lowry, and De La Rue. Now I have this slide, the father of the gaseous sun, one of the fathers of the gaseous sun. Now, it's interesting that I call him a father of the gaseous sun because if you read this quote, you'll see that Kirchhoff actually believed that the sun's photosphere was either solid or liquid. He didn't believe it was a gas at all. But the problem is that Kirchhoff gave Kirchhoff's law. And when he did, when he wrote this law, which we just discussed in the previous talk, he permitted the astronomers to make the sun a gas. So, according to Kirchhoff's law, as long as the sun can be considered to be enclosed, then it must contain black radiation, even if it's gaseous. Obtaining a thermal spectrum is not a difficulty, okay? Yet, was Kirchhoff's law actually valid? Do arbitrary cavities really contain black radiation? And if so, why are all the laboratory black bodies always constructed from nearly ideally absorbing materials? So clearly, this wasn't right, as we discussed in the previous talk. Now, I didn't give this little experiment. It just turns out, you know, this talk was ready first, and then I was able to give the talk on Kirchhoff. And I was only going to discuss this one in this talk, so I'll discuss it now. So here's an experiment proving that Kirchhoff's law is not valid. So what we're going to do is we're going to have an inner box and an outer box. In the inner box, we'll make it out of a perfect conductor. Its emissivity is going to be 0. Its reflectivity is going to be 1. We leave that box open. In the outer box, we're going to make it out of a perfect absorber. Its emissivity is going to be 1. Now we're going to take that outer box and we're going to plunge it into a helium bath. Now the inside box is sitting on the floor of the outer box. Now when I put that outer box into the helium bath, what happens? The whole thing's going to go to 4 Kelvin. Now the outer box, being a perfect emitter, is going to give me photons at 4 Kelvin. So I'm going to get a black body spectrum at 4 Kelvin. Now what do? I close the inner box. I get rid of the helium. What happens? Everything goes up to room temperature. Now when it does, what's going to happen? Through conduction, the inner box, using conduction, is going to go up to 300 Kelvin. But now that door is closed, and it's got 4 Kelvin photons trapped in it. It cannot produce 300 Kelvin photons because its emissivity is 0. The outer box, of course, will produce 300 Kelvin photons, and so it'll become filled with black radiation. But remember, Kirchhoff's law said both boxes were supposed to contain black radiation at the temperature of interest. And now they don't, so Kirchhoff's law is broken. Arbitrary cavities do not contain black radiation. And of course, as I mentioned in my Kirchhoff talk, these papers have all been submitted, and the last one is not just submitted now, I submitted it this week and it was immediately published, so that's already published. So the gaseous model of the sun cannot account for the thermal spectrum. That is the only proof that's required to establish condensed matter. I wrote 40, but you actually only need this one. I really don't care about the others because this one has a lot of physics in it. But we'll throw in the others because sometimes people can't understand this one, but they see the ripples on the sun and they can understand that one. Now, who are the notable advocates of a liquid sun? The first was Kirchhoff himself, and unfortunately, his law undid it. Lord Kelvin was also a prominent advocate of the liquid sun. And this is reviewed in this paper. I think you guys would enjoy the history paper of how the sun became a gas. But the most notable advocate of a liquid sun was James Jeans. And he was a phenomenal scientist. And the story of James Jeans' sun is described in the follow-up paper to the first one. Now, there was an interesting character called Hastings. And Hastings, he wrote in 1881 he wanted graphite on the sun, but he knew he couldn't get it. So granting this, we perceive that the photosphere contains either solid or liquid particles hotter than carbon vapor, and consequently not carbon, because he knew he couldn't get carbon. But at any rate, we are sure that the substance in question, as far as we know it, has the properties that are similar to those of the carbon group. So he wanted something that behaved like carbon, but he knew he couldn't have it in 1881. So this guy was pretty smart back then. Now Jeans, he had a different approach. Why did the liquid sun die? He thought all the stars were liquids. And the reason it died is that he thought the sun was made of uranium or radium. Well, when it was proven that the sun was mostly made out of hydrogen, of course, he was out of a building block. But he did properly recognize the phase. And he says there's only two possibilities for stars. They can only be liquids or gaseous. There's no intermediate, okay? One of the first points to make is that the sun is condensed matter. It has a true surface. And solar emissivity must be accounted for by the presence of a true structural lattice. And here's my nice New York Times article cited for you guys. Now, remember, I was trained as an inorganic chemist, and you learn in chemistry that hydrogen is the little cousin of carbon. So isn't that convenient? Now, right at the time that Jeans was losing his building block in the 1920s and had to abandon his liquid sun, if he had read Wigner and Huntington's paper, he would have had the solution. Because Wigner, who's a Nobel Prize winner in physics, said that at high temperatures and pressures, hydrogen will become metallic. It'll assume a structure which will be condensed. So let's read exactly what he said. The objection comes up naturally that we have calculated the energy of a body-centered metallic lattice structure only, and that another metallic lattice may be much more stable. We feel that the objection is justified. It is possible, however, that a lattice-like lattice has a much greater heat of formation and is obtainable under high pressure. Diamond is a valence lattice, but graphite is a layered lattice. So here what happens is Wigner and Huntington in 1935 tell us that hydrogen can assume the graphite form. Then Neil Ashcroft, which is one of the top condensed matter physicists in the world and a great authority on metallic hydrogen, wrote a paper which he forwarded to me in 1991. And in that paper, Neil wrote, on a little reflection, it is apparent that all the quantitative remarks just presented on the band overlap state in dense hydrogen, by the way, he just recently forwarded to me. On a little reflection, it is apparent that all the quantitative remarks just presented on the band overlap state in dense hydrogen could have been made with minor modifications about graphite, the tetravalent hexagonal band overlap 1 atmosphere semi-metal. Accordingly, it is instructive to examine the known optical characteristics of graphite. In the visible range, graphite appears black. To some extent, these characteristics are reported to be shared by very dense hydrogen. One possible choice for the structure of dense hydrogen consistent with hexagonal symmetry is actually a graphite-like arrangement. And then, lo and behold, some people are working while the rest of us are sleeping. And this group, actually recently created dense hydrogen with a graphene structure. So the spectral signature of the strongly interacting hydrogen molecules is consistent with the presence of graphene-like sheets, a configuration predicted in early calculations on dense hydrogen. So now we have something quite close in the laboratory. So again, this is the structure that we're looking for. Now, what have I said? I said the photosphere is comprised of metallic hydrogen, which has assumed the graphite-like layered hexagonal lattice. The internuclear distances within this lattice are such that the material is semi-metal, not very metallic, not highly conductive. So the photosphere cannot be highly conductive. Why do we know that? We know that from its emissivity. Remember, its emissivity is high at normal and then drops with angle. So that means you can't make this a conductor, okay? But as you go inside the sun, then there's compression, and so the lattice gets compressed. And sunspots, faculae, and the convection zone are comprised of metallic hydrogen, which has adopted the same graphite light layered structure, but this time it's type 2. In this case, the internuclear distance is decreased, such that the material becomes highly conductive and able to support both strong magnetic fields and the solar dynamo, which cannot be correctly explained in the gas model. So we have a solar dynamo. How do we get it? To get a dynamo, you need a combination of conductors and insulators. You can't get that in a gas. The solid solar core is likely to be composed of metallic hydrogen, which has adopted a body-centered cubic. This was first proposed by Professor Setsuo Ishimaru. The corona possesses both free ions and atoms and sparse distributions of metallic hydrogen, which are type 1, which have been ejected from the solar atmosphere into the solar atmosphere from the body of the sun. So there's emissions. I just showed you a coronal emission in the, a coronal mass ejection in the movie. So the sun is sending stuff up into its atmosphere. The chromosphere possesses both free ions and atoms and sparse distributions of dense hydrogen, but that is not metallic hydrogen. It's molecular in nature, and it results from condensation reactions in this region. And the transition zone does not exist. So this is what we're saying in this model. The center, if you look at the center of the sun, I think the body-centered cubic makes the most sense for the structure. And of course, this is open to debate. You can come up with your own ideas, but I think this one makes the most sense. Now, in the photosphere, we have the hexagonal layered structure with hydrogen. If you go inside the sun, in the sunspots and the convection zone, we have the same structure, but now it's compressed. See, the internuclear distance is larger here than here. So this is more compressed. When it goes compressed, the conduction gets very good. The quantum conditions are fulfilled for good conduction, so this becomes a conductor. Whereas here, the quantum conditions are not fulfilled, and this could even be an insulator or semi-metal. Now, in the chromosphere, we'd have a structure that might be something like this. This is proposed in Ashcroft's paper, not for the sun, but generally in reviewing dense hydrogen. So he has a hexagonal structure again, but now the hydrogens are molecular in nature. So what happens in the sun is that you're actually fighting to recapture the hydrogen in the chromosphere, and then that enters the sun and then gets recompressed into metallic hydrogen. So the continuous spectrum, so the chromosphere has a continuous spectrum. And because it does, that's direct evidence that this region contains condensed matter. The chromosphere is likely to be a site of hydrogen recapture and condensation in the solar atmosphere, as evidenced by its emission spectra. The chromosphere thereby acts to help conserve the mass of the sun by harvesting some of the hydrogen atoms and protons which have been released into the solar atmosphere. So here's an example of, I just love stumbling on just a beautiful paper, you know? You're not really looking for it, but it just falls right into your lap, like this paper by Ertl, who won a Nobel Prize in chemistry, I don't think for this work. But here's an example of condensation reactions in clusters. So you have two metal clusters with different amounts of atoms in them, and when they combine, they make an activated cluster. That's why there's a star there. And then it relaxes, that activated cluster relaxes by emitting a lone atom in activated state. And then that atom then deactivates by emitting a photon. So we know that in the chromosphere, we have light emission. Okay, we have emission lines from many, many types of cations and atoms, and it will adopt the same ideas. So what we're going to say, this is the simplest idea we can adopt. We have hydrogens of different numbers of hydrogens in both groups. They come together in activated form. That gets deactivated. You lose a hydrogen, and the hydrogen you lose is active, and then that activated hydrogen then gives rise to the light. Now this can be, if you read the paper where this is described, you will see a very beautiful explanation of why we have helium triplet lines in the sun that are so intense. And in order to get a helium triplet line, remember, you need about 55 electron volts to get those lines. And the chromosphere is only supposed to be at 5,000 Kelvin, so how do you get 55 electron volts there? Well, what the current models say is that, well, the triplet lines of helium are excited by photons coming from the corona. These selective photons come just with the right frequency and excite triplet helium. But if you read my paper, you will see that helium is a great way to harvest hydrogen. And it's known that if you have helium and hydrogen mixtures, when you have such mixtures, you get ions, you get helium hydride cation, and you can get activated helium hydride, and I believe we have both in the sun. These things are ubiquitous in mixtures of hydrogen and helium. Now here's an example for magnesium. You might ask, well, why is it that it's magnesium 2 lines that we see? Why do we see calcium 2 lines? Why don't we see the calcium 3 lines, which of course the calcium 3 lines correspond to calcium having lost 2 electrons, right? So why is it that we don't see the calcium 3 lines? Why do we see calcium 2? Well, here's an explanation from condensation reaction, the same kind of scheme with magnesium. So now we know magnesium hydride is known to exist in the sun, on the disk, and in the sunspots. So what happens is that magnesium hydride then condenses with a condensed hydrogen structure and then donates a hydrogen. That structure becomes active. It donates a hydrogen. It kicks off the magnesium. The hydrogen structure grows by 1 hydrogen atom. The magnesium is now active, and now you get an emission line. This, by the way, I had missed something very important in these reactions, and my young son, who's an undergrad at OSU, said, "Dad," and I didn't listen to him. He kept telling me, "Dad, you're missing something." And 3 times he tried to tell me until finally he convinced me I was missing something. You could read my son's paper. It's a beautiful addition to this problem. Now, how about the corona? Well, we know that the corona has white light. It emits in white light. Now, how do they explain that in the gas model? Well, what they say is we have relativistic electrons in the corona, and those relativistic electrons are scattering the photospheric light. Now, in reality, we know that the K corona is becoming, the spectrum of the K corona is indicating that the temperature is dropping with distance. If you look at the continuous spectrum of the K corona, it's reddening with distance. That means the temperature is dropping away from the sun. But all of you know, of course, that we can have iron 25 up there. Let's say quite high up, 1 radius up from the solar surface, you can have iron 25. You have these enormous ionization states. How do you get them? So first, the continuous spectrum of the corona does not represent photospheric light scattered by relativistic electrons. It constitutes direct evidence that the corona is both self-luminous and relatively cool, an apparent temperature associated with vibrational degrees of freedom which are no greater than that of the photosphere and which decreases with elevation, not increases. The presence of highly ionized species in the corona are not associated with temperatures in the millions of degrees, but with the presence of condensed matter in the corona, which possesses an elevated electron affinity, which can strip the atoms of their valence electrons. So you've got metallic hydrogen there, it's starving for electrons, and if you're an unfortunate iron atom that comes near it, you're going to get stripped of all your electrons. The corona is the site of electron recapture, and it works to help maintain a neutral solar body. Now, one of the big problems in the sun has to do with the solar wind, and I want to stay on time here, has to do with the solar wind and the solar activity. If you ask a solar physicist, why does the sun go active? Why do we have a solar wind? Now, the solar wind, I discussed it in my paper, and I consider the current explanation a violation of the laws of thermodynamics, and you could read the paper. So basically what we have is that somewhere outside the sun, in the atmosphere of the sun, you have to drive energy processes onto the sun. So you get flares. Why? Because you have magnetic energy transfer onto the surface. So now I got energy flowing towards the sun. But in the solar winds, I have to have heat going away from the sun. Well, you can't have the heat going in both directions. It's either going towards the sun or it's going away from the sun. So their explanations for solar wind doesn't work. But if you read this paper, Liquid Metallic Hydrogen 3, what do you see? I also wrote a paper on helium in the sun because, of course, the solar physicists are telling us that the sun actually has a reasonable amount of helium. And as you know, helium is one of the 3 pillars for the Big Bang, right? So the microwave background is one, the redshift is another, and helium is the third. So helium in the sun is very important to the astronomers because it's also linked to cosmology. But look at what the sun is doing with the cycle. What is it doing? When it's quiet, so you look here at the top here, the top of the figure, in 1996 and 2006, that's when the sun is quiet. So when the sun is quiet, there's hardly any helium-2 lines on the outside. It's quite silent. But when it goes active, it starts expelling helium. So why does the sun go active? Because it's degassing its non-hydrogen elements. It wants to kick everything out. So when the sun is quiet, at the poles, you have coronal holes. And in those coronal holes, material is leaving the sun at constant rates, and so now the sun is it's able to degas its poles when it's quiet. But it can't do anything about the equator. Any atoms that are non-hydrogen, made in the equator of the sun, they're trapped. They can't get out. Why? And I'll show you this in a minute. So because they can't get out, I'll show you in a minute. So because they can't get out, the sun has to go active to degas the equator. And so that's why we see the sun going active. So here's an example that we know from graphite again. Graphite can make intercalate compounds. Since I'm an inorganic chemist, I know this, okay? Now, how does an intercalate compound work? Well, what happens is you have so we're going to assume that our metallic hydrogen, which can have the same structure as graphite, also can do this. Now, what I'm saying is that because inside the sun, you want to keep these metallic hydrogen bands conductive. You want to keep these layers conductive. We've got electron flow going through there. So if you have a nuclear reaction, you create an atom that's non-hydrogen. What happens is you kick it into the intercalate region. So you end up building these atoms in the intercalate zone, and then you have these hydrogen sheets. Well, now what do you have? Now you have your insulator that you need for your dynamo, and you have your conductor, okay? But the sun, if you look at the elements that are in this region, these atoms, they can't translate in this direction. They cannot go through the planes. But they have almost free motion in this region. So in the poles, if you orient the poles this way, now those atoms can go out, and so now during the period when the sun is quiet, you have atoms escaping at the poles. And in the equator, you can't do that because now you say, so I almost have to draw this for you, but in the equator, the hydrogen planes are on the surface of the sun. They're aligned parallel to the surface of the sun. So now the atoms are trapped inside. So what happens is that when you get activity, these atoms can change from a solid phase to a gas phase. And when they do, that pushes the layer up. So that's why we get solar activity and the atoms leave. Okay? So the sun tries to degas its equator, and that pushes the layers up, and this is why we were getting the sunspots. Now there's something very interesting about this, and that is that this idea very easily explains why do we get red giants. The reason you get red giants is you have a star, it has a real lattice, it has a hydrogen lattice, and that hydrogen lattice doesn't want the other elements. So it starts making these layers, and all of a sudden, all these layers decide to go in the gas phase at once, and all of a sudden, paf, you're going to get a red giant. Now, if you had all these atoms in one region of the sun, so let's say, for instance, the sun has managed to put these atoms in one layer. There's a lot of non-hydrogen atoms in one layer that are in the solid state. And all of a sudden, these go to gas phase. Now you'd get a supernova. So I'd like to acknowledge some people. My son Luke, he does all the drawings for my papers, and also the one paper where he corrected his dad. Well, he didn't correct me. He added a new idea that I had missed. And so I'd like to acknowledge my son Luke. I have another son also who contributed a paper to this. Bernadette Carstensen, she's an artist, and she's done lots of sketches for me, all the graphites that you see. Of course, my own department, as you know, this started from the 8 Tesla scanner, and I went into this. Hard for a lot of people to understand, but my department has kept supporting me for all these years, and I'm grateful for them. And of course, the editors of Progress in Physics, without that journal, I would have never been able to publish many of these ideas, and they have come up with the book Inside Stars. And of course, there's a lot of astronomers that are working out there, and they're getting fantastic data for us. And I'd like to recognize the data that I used, both from SOHO and the Swedish Solar Telescope. Thank you very much. In 1865, we've thought that the sun does not have a surface. Now, actually, some observational astronomers didn't agree with that, and there were arguments about the sun, did it have a real surface or not. You could find papers into the 1900s. Until then, there were papers by Schuster, Schwarzschild, and of course Eddington, and the sun then became fully gaseous, or been viewed mathematically as fully gaseous, and the observational astronomers just lost that battle. So today, if you look at the present model of the sun, we have a core, and in the core, it's thought that all the photons are produced. And why do we know that? Because of Kirchhoff's law. Of course, I just showed you that that is no longer valid. You cannot produce photons in the core of the sun. And then we have other layers, the radiation zone, the photons are leaving the core and they're radiating out, then we have convection zone. And eventually, for the gaseous sun, it takes millions of years for photons to finally escape here and give us an emission spectrum. Now this can be justified using Stefan's law, the center of the sun being very, very hot. If you say that the amount of photons that you get moves with temperature to the fourth, and you really believe that the surface here is at 5,000 Kelvin, and that's temperature to the fourth, you'll see there's an enormous amount of photons produced here. So this has to be considered enclosed, and that's how they felt that the sun could follow Kirchhoff's law, that it could be considered enclosed. Now the question for us is, does the sun really have a surface? And there's so much evidence about it, and people have said it a long time ago. There's no question the sun has a surface, and as soon as it has a surface, it cannot be a gas. So we have prominences and coronal mass ejections that can rise from the surface and come crashing back down. They represent real structures, and they are not optical illusions. So this is a little movie here, and you're going to see a coronal mass ejection. It comes back down, and it crashes onto the sun. And when it does, you see all these bright points lighting up. So this is a collision that's taken place. There is a boundary there. It's not just an optical boundary. It's a real boundary. So I'll let you see it again. That around 1965 is when the idea that the sun was a gas was really born. Now for Herbert Spencer, it wasn't fully a gas. It was kind of a bubble. It was a gas inside and it was condensed matter outside. For Fay and Secchi, the sun was a gas that had floating solid particles on the photosphere because they wanted to have the thermal emission spectrum. But what happened with Fay is something quite important. It's here that the sun lost its surface. So when you talk to an astronomer, they tell you, well, the sun doesn't have a real surface. It's an optical illusion. And of course, we can use mathematics to justify that. But the idea actually goes all the way back to Hervé Fay in an article he wrote in Le Monde in 1865, which I translate here for you. So then the exterior surface of the sun, which from far appears so perfectly spherical, is no longer a layered surface in the mathematical sense of the word. The surfaces, rigorously made up of layers, correspond to a state of equilibrium that does not exist in the sun. So surfaces do not exist in the sun. This limit is in any case only apparent. So since 1980, Well, thank you once again for enduring me. I guess this is 3 times now. It is a privilege to talk and to have an opportunity to address you about the sun. I'd like to dedicate this talk to my mother, Jacqueline, and actually she, maybe like a lot of our mothers, taught me the most important lesson. And we're all trying to learn lessons here, but the lesson she taught me on her knee was to love. Now, when we consider the sun, currently it's viewed as a gaseous plasma, and I'm going to advance that from the photosphere down, or to, after hearing David's talk last night, from the photosphere in. I didn't hear the whole talk, unfortunately, just the part, but from the photosphere in, the sun is condensed matter. And in the corona and the chromosphere, you have a combination of condensed matter and plasma. Now, the first proponent, actually, of the gaseous sun was Herbert Spencer. He was a very prominent evolutionist. His works were largely ignored by astronomers, but he got into quite a few little scuffles, and if you're interested in the history of how the sun became a gas, the citation is listed here. But the real person who gave us a gaseous sun actually was Father Angelo Secchi. He was just a spectacular astronomer. And if anybody has a chance, online you can see his books, Le Soleil, they're in French. And, but even if you can't read the French, look at the figures. They're phenomenal. And also Hervé Faye. So the sun really became a gas in the minds of these men in the 1960s, and many prominent men of the time in physics. So we can say